We are delighted to have an old friend back with us, Brandon Reddell. And Brandon, you qualify as an old friend because this is your third time back with us, and we very much appreciate your both expertise and your support of our ministry. For those of you who don't know Brandon, he has degrees in physics from the University of Texas and an MS in applied space physics from Johns Hopkins University and a PhD in physics, which is high energy space physics from the University of Houston. He currently works at NASA, the Johnson Space Center, where he supports all the human spaceflight programs in the areas of ionizing radiation, which is produced by galactic cosmic radiation, solar particle elements, and trapped radiation belts around the Earth. Brandon also serves as an adjunct professor of astronomy at Los Angeles Pacific University and occasionally in physics and astronomy at the University of Houston at Clear Lake. Additionally, he is an adjunct professor in the School of Divinity at Regent University, where he teaches cosmogony and astronomy design in the universe. So, Brandon, thank you so much for coming back. And tonight he will be discussing some additional features from what he had discussed before of a solar system that may help explain Earth's unique elemental abundances that are essential to life. So, Brandon, thank you, and we'll turn it over to you.
Alrighty. It's a pleasure to be back. Hopefully you guys can hear me.
Yeah.
Let me share my pitch here real quick. So, yeah, I hope everybody's doing well. Things are good here in the Houston area, though we have a potential tropical storm forming tomorrow right off the coast. So a lot of rain here. So hopefully my internet holds up. It's actually not raining at the moment, so we're good. Uh, yeah, so I'm here again. This is kind of like a part three. And this presentation, I'm going to kind of give you a quick overview or summary of the highlights from the previous two talks because they sort of roll up and provide the motivation really for this talk. And so that's one of the purposes of this talk. The second one is to show, right, we're talking about design, right? And so I wanted to just sort of provide examples that you can really pick on any of these topics and do a deep dive and uncover a lot more design information. And so I want to talk about that in the context of our solar system, and in particular, maybe where it formed within the galaxy. And so we'll talk about that. Okay, so here's the outline of the talk. Um, so I'm going to review habitability. That was really the first talk. It was really based on Hugh Ross's book, Improbable Planet, but that's certainly uncovered in a lot of mainstream research as well. Then I moved into the second talk I'd done for you guys was on galactic habitability, right? And so within there, the focus will kind of you'll see in here in a minute, but we'll morph into understanding what the co-rotation radius is, and then what are the implications of a solar system forming like outside of that or at that location, right? The Earth is pretty close to that, and that, as we talked, if you remember last time, that's an optimal location. Talk a little bit about it says CCSN, that's core collapse supernova. It's like a type 2 supernova, right? The one that we all know about, big stars blowing up, right? And so you probably know that it's these type 2 supernova that really create a lot of the heavy elements in the universe. And so um, as we'll talk about the abundances of elements on Earth, what are the implications of having supernova close to us, right? To help provide the elemental abundances we see in our solar system. And this have implications for our location, depending on what we know about our current location. You know, further out, we know there's less heavy elements. Further in, there's more, and so forth. And kind of wrapping all this up, I'm trying to get more about evidences for design, right? And these are topics that we can use to talk to people that are interested in this, number one, but also number two, to show that It takes a lot of these, all these things stacked on each other really build a cumulative case that, you know, kind of defies the odds, if you will, and really does point to intelligent design. And so that'll be how I conclude this talk. And feel free to interrupt him, if you have questions. So it's been a while since I talked a lot about these topics. So hopefully I remember everything. But if you remember in our first talk, these are really the key elements, except probably that bottom right one. But when we talk about a planet, habitability on Earth, um, there's something called the habitable zone that comes up all the time, and it's more than just the liquid water habitable zone. We found out that you know the type of star produces the a flux of ultraviolet light, and so that plays an important factor in cellular processes, certainly needed for cellular life and so forth. And likewise, the same idea behind photosynthesis. And then the planet with an atmosphere, particularly oxygen, that does really nice when you dissociate oxygen and produces ozone, right? Which is produces a protective shield to help shield out some of the intense ultraviolet light, right? Some ultraviolet light is bad, but some is good. And then we also looked at planetary rotation rates and obliquity, right? Those have to do with the how fast the planet's spinning and the tilt, right, for seasons and so forth. And that also really controls the global atmosphere. And so all of these things are important to have when we talk about habitability, right? These things are all control factors. And then the closeness to the star, and even if you have a moon, right, tidal zones. And then we looked at really the size of a solar system, which really depends on the star type, but that a lot of people call it the heliosphere, right? That's sort of the influence of the sun's field. Um, when you have a solar system in the midst of giant molecular clouds that they can compress and expand, let's say, the heliosphere. So that has sort of implications on very long time scales. And then in recent times, we've had a few satellites looking at not only Earth's magnetic field and electric fields, but also around Venus. And they've made really good measurements to show the importance of an electric field of a planet and how that helps in the absence of a magnetic field, potentially uh, accelerating atmospheric loss, right? And so that's another area that we need to look at when we're considering planetary habitability. And then finally, really closer to my day-to-day work is what we call space weather effects. Um, I actually even published an article a while back on, I think it was Jeff Zwering's blog, but a lot of the a lot of the talk these days are on exoplanets is looking at um, not only like obviously finding the number of planets, but most of them are around M dwarf stars, and they're very, very active stars, much more active than solar type stars, which are G type stars. They're anywhere between 100 and 1,000 times more active, and so there's a lot of research. You can go look these things up, but for such planets around small M dwarf stars, the planets are closer in. They're going to feel the much higher effect of space weather on the planets, and potentially uh, most of these planets we shouldn't expect to have any kind of atmospheres. And so these are all problem areas. And so that's what we look at, like from within a solar system. And this is not a this is not like all of the items, right? These are the type of habitable conditions that we know about, certainly with Earth. Right. If you notice, I didn't mention anything about planetary magnetic fields. Uh, you know, and the sort of the type of planets, rocky and gaseous planets, and so forth, and neighboring planets, right? There's a lot more factors, but in terms of habitable zone, when you look at how far you are from the star, right? These are some of the big players that really control habitability. And then in the second talk, we went in to look. This is actually a slide I pulled from that talk. Kind of stepping out a step, if you will, on scale size. And so when you look at our galaxy, I'm not going to read all of these, but the big bullets here, right? The galaxy must be in a stable location for billions of years. Most galaxies are in galaxy clusters. And so just like if a solar system's too crowded, there's gravitational effects. It's just this exact same thing. Gravity can act and interfere with other galaxies, right, if they're too close and cause instability. Uh, Most clusters, even within and outside, cluster together, and so there's something called a local neighborhood, and the number of components in the neighborhood, the separation. Um, if you think of like food for a galaxy, right, we call those dwarf galaxies, right? They infuse energy and uh, elements and dust to help drive stellar production in certain galaxies. So you have to have all these factors in place to produce like stable galaxies. And then we talked about three type of galaxies, right? There's broadly speaking, there's elliptical, irregular, and spiral galaxies. And of those, really certain type of barred spiral galaxies are the only really stable ones on time scales of billions of years. And elliptical galaxies and irregular are very chaotic in nature. There's no way you can really have on those timescales stable solar systems. So that's very problematic. So we shouldn't expect to find habitable planets, in these type of galaxies. And by the way, of all the galaxies, when you're looking in clusters, there's research that suggests that less than 10% of those are spiral galaxies. Uh, and going back actually to the type of stars in these galaxies, 85% of the stars on the main sequence are M dwarfs. And so those are the ones that I was telling you that are very hard to produce stable atmospheres. You have tidal effects and very um, active stars that would just drain the atmospheres and so forth. So just those two factors alone eliminates quite a bit. And so they don't talk about this in the mainstream science world. I mean, people know this. I mean, you can do Google search, look up the main sequence, and you can see the categories of stars and their percentages. And then in this red box here, this is kind of the motivation that kind of peels off from the previous talks into the current talk. And so I wanted to look at I think we actually hear it, and even in this forum, we had questions on the co-rotation radius, if I remember correctly. And I'll talk about that here in a second. But the right location within a galaxy is very important because we are finding planets around other stars, but that just because they're there doesn't mean they're habitable. Um, if you remember, co-rotation. So this is an artist rendition of our galaxy, kind of like a top view, and this black circle here on the right is the distance from the center. Um, it it's our sun orbits our galaxy at at this distance. It's about 7.7.5 kiloparsecs from the center. Uh, the co-rotation distance is where the revolution of the sun around the center of the galaxy equals the rate of rotation of the spiral arms. And so that's important because whether you're further in or further out, the sun and hence our solar system would experience the passage or pass through um, other solar systems, other dense molecular clouds, and nearby stars, and be lots of gravitational disturbances. So it's really, if we're talking about habitability and long times on planets that have those conditions, for life to thrive, you need this being this type of location for quite a long time uh, if you want life to survive. I'll just put it that way. Um, the what's interesting with the co-rotation, uh, not only do we avoid the frequent arm crossings, um, this distance, we're far enough from the center of the galaxy where the radiation emanating sort of out from the center, right, is not too high, but it's just enough because we do need some of that energy. And you can think about it, if you're near the very edge of our galaxy, we're not going to get enough of that radiation. Um, that little graph at the bottom is showing the metallicity plot as a distance from the center of the galaxy in kiloparsecs. Metallicity is what astronomers, when they talk about that, it's really just all the elements heavier than hydrogen. Sometimes they throw helium in there too. So we're talking about like carbon, oxygen, and everything else above that. And so high metallicity means high of these heavier elements. And what we see at this dotted line here uh, is it might be off a little bit. I think it's 7.8, but it looks like it's above 8 here. But around 8 kiloparsecs is sort of like a dip in the metallicity. It's not the lowest point, right? Because we need some of that, but it's not the extreme either that happens out around 4 kiloparsecs. And so these are interesting features. Now, that alone doesn't really tell you anything about habitability, but they're just factors to think about because um, there's certain expectations that come in with metallicity given our location. And do we really see that or not? So a couple more pictures. Again, the left picture is really the same thing. I took this. This is actually off of ESA, a European Space Agency website. Really, what I kind of want to transition here, looking at the right side. Uh, Obviously, this is an artist rendition, but when we look at our galaxy from the edge, you know, most of the material is in the galactic disk. Um, it rotates around. Now, all these things that are kind of floating above and below the disk are globular clusters. They're clusters of stars, tens of thousands of stars or more, and that's important. The other type of clusters that are primarily in the disk are called open clusters. So globular clusters can be all around um, our let's say our halo of our galaxy. So that means in the bulge, outside the disk, still orbiting around in our galaxy. A lot of them are in the disk too. Now you can't see them in this picture, but there's some in the disk. And globular clusters are much, and I'm going to talk here, give you a little bit more detail, but there are really more stars that are more gravitationally bound together, whereas open clusters are usually less stars, and they're not like balls of stars. They're kind of spread apart, but they still interact gravitationally. And so here's some actual pictures. I actually took these two pictures on the left. These are you can go out if you go to a dark sky site. Hercules is out now. The cluster, it's rising in the east. I was just out last month looking. I took this one a couple years ago, but these are examples of globular clusters here on the left. Probably hundreds of thousands of stars in the Hercules cluster. What's nice in Texas, because we're far enough south, we can look at Omega Centauri, which is this bottom cluster, and it's the biggest. Actually, I think a friend of mine took this picture, but they all look very similar. But what you see here is a lot more stars. I think it's on the order of millions of stars in this, maybe 2 million stars. And just so you know, you can actually see this with your eyes if it's dark enough. When you're looking kind of low on the southern horizon, you see this kind of patchy area, and it's about the size of the full moon at a distance, angular width. But certainly through binoculars and low power telescopes, this is what you would see, and it's pretty amazing. But there's literally millions of stars sort of clumped together. The other clusters that are more prevalent are these things called open clusters, and they're just like the name says, they're open, they're spread apart. They're still gravitationally connected to each other, but they're not. They're much fewer stars, usually tens to hundreds, maybe 1,000 stars at the most. This is a picture of M93, and on the background of all the stars in the distance, right? It's kind of hard to see, but all these blue dots here that are kind of bigger, and a couple of these yellows or reddish stars, these are all about the same distance from us, and they're gravitationally interacting, and so this is an open cluster. Okay. Now, uh, so this is a table I pulled out of Hugh Ross's book Improbable Planet. And when you start to look at Earth, now let's kind of go back to our solar system and Earth in particular. Uh, so it's often quoted that Earth has a unique, especially by RTB type folks, right? But it's well known in mainstream science too that Earth does have, and when I say Earth, also our solar system, uh, a rather high abundance in certain areas relative to the average we would expect in the Milky Way. Now, this is a really hard quantity to measure. Hugh Ross has this funny term here where he says, like these factors here are, it's kind of like a double reference. It's Earth's crust relative to magnesium and the crust relative to the Milky Way galaxy. Magnesium in Earth's crust is has about the same concentration as the kind of like the average everywhere you look in the Milky Way. And so by taking kind of referencing it to the magnesium to the galaxy, he's come up with a lot of these factors. Um, and and we'll talk more about this table here in a minute, but the key ones I want to point out because I'm going to talk about these later is aluminum, uh, uh, uranium, and thorium. Right there, those are pretty high, a couple hundred times higher than on average than what you'd expect anywhere in the Milky Way. And then the table on the right, and again, I'm going to talk about this here at the end, but he calls these vital poisons. Right? These are elements vital for life, and too much or too little can kill life. And so on the face of it, that again, this doesn't necessarily say it's unique, but it does beg the question, why would there be such a deviation from, let's say, the average, right? If you could really measure that well. And so generally speaking, the Earth and the solar system by extension has higher elemental abundance than expected for our current location. And so for many years, and I'm going to show you some papers here, uh, it's been speculated that, whenever our solar system formed, right, close to 5 billion years ago, it's probably in a different location because the metallicity locate we're at our location doesn't support that. Now, there's a couple observations here, and these are references, mainstream science. The very first bullet, right? The majority of stars, 90%, are within the disk of our galaxy, are formed from clusters of 100 stars or more. Right. This is from back in 2003 in the Journal of Astronomy and Astrophysics, annual review of astronomy and astrophysics. Uh, most stars, while we look and see a lot of clusters, we also see a lot of individual stars. So a lot of them are, they interact gravitationally and they're kicked out a lot of the times. So, but the point is, most stars form from molecular clouds that contract. And so you get groups of stars, right? There's always a cluster of stars, and then something happens and they get kicked out. Now, there's three observations that convince most astronomers that our solar system was formed in a cluster of at least 500 stars, right? Um, I'm not going to talk about all these, but I'm going to give a quick overview on a couple and then focus on the bottom one. But the three real key pieces of evidences, I don't know if you've ever heard of trans-Neptunian objects, but these are kind of like large asteroid kind of objects, maybe even Pluto and Charon, right? Well, there's a lot of debate on that, but have very high eccentricities that don't match anything that came from like a solar system formation, right? It's inconsistent. It's like either they came from somewhere else, or something passed by and disturbed them to create these highly inclined orbits. And so that's always sort of been an active area of study, is how to explain that. And then there's a whole area of solar system sort of geochemistry that looks at the isotopic composition of pre-solar grains, right? The dust, the earliest formation of particles in our solar system, um, uh, and understanding their concentrations. And it's kind of related to the second one here. There is an abundance of um, elements, right? Some of those deltas that I showed on the previous chart uh, are different uh, given the location, right? Trying to understand when you look globally across our solar system and average solar system, given the metallicity, what we should expect. Scientists actually, there's been a few missions on spacecraft that have gone. We've certainly collect meteorites, but we have a lot of samples and they can do isotopic studies. Um, and then finally, the third one is really focused on short-lived radionuclides, and that's kind of what I want to spend more of my time on this talk. But in particular, aluminum 26 and iron 60. Um, those are there's a lot of papers talking about these two because they're helping researchers understand the earliest moments of our solar system. And they're called short-lived radionuclides because they're no longer present, right? In these pre-solar grains, right? They were once there, and so you may be wondering, well, how do we know? How do we know they're there? Were there? Well, when these radioisotopes decay, they decay to more stable life form, elemental forms. So, for instance, aluminum 26 decays to magnesium 26. And so by studying these daughter elements, right, they know the nuclear processes, they can understand the original amounts. And so I don't want to go too deep dive because there's a lot of geology here. It's kind of a little bit outside my area, but I wanted to kind of just tell you in an overview what we're sort of expecting, trying to connect these to not only our elemental abundances in our solar system, but some research that might have showed that our solar system forms closer in. So, going back to these papers, this is from 2009, Stellar Sources of the Short-Lived Radionuclides in Early Solar System. Now, these are just quotes from within the paper, right? They're too technical to go over in a talk here. As you can see in the middle here, short-lived radionuclides, they talk about aluminum 26, and there's a whole bunch more, and then iron 60, right? There's more than just those two, but these are like kind of the most abundant of these they can study. But they said back in 2009, we conclude that the intermediate mass AGB stars and massive stars in the range of 20 to 60 mass of the sun, right? 20 and 60 times the mass of the sun, right? These are large stars, right? The type that go supernova are the most plausible sources. In this particular talk, I'm not going to talk too much really about the AGB stars because um, they may produce sort of the lighter elements, and I'm really wanting to focus on these heavier elements. But this is an area, if you're interested, you can certainly go off and look. AGB stars are it's the asymptotic giant branch on the Hertzsprung-Russell diagram. It's just stars like our sun go through a bunch of phases, and later on in life, when they're past the red giant phase, they're shedding its outer atmosphere under high winds, blowing off certain elements and things like that. But they're not strong enough to produce the heaviest of uh, these heavier elements. In 2016, another paper published in Annual Reviews of Astronomy and Astrophysics. This is more of this is a very long paper because it's an annual review, but in here they spent a lot of time talking about the isotopic composition of the pre-solar grains, right? Again, I just wanted to mention these pre-solar grains think about the earliest dust particles that formed in our solar system, and they're dated to be just over 4.5 billion years old, right? So, uh, I think ours, 4.55. These are closer to 4.6 maybe. Um, so when gravity takes a whole, right? You get small things and then gravity pulls things together and so forth. So it's those first things that form out of the molecular clouds are pre-solar grains. But again, here, this particular author, right? He references the stellar winds from the AGB stars, but in yellow here, right? Or explosions from core collapse supernova shortly before the formation of the solar system. And so, um, the point is I'm trying to show you that this is not anything kind of new. This is nothing outside of mainstream science. This is well established science that astronomers are genuinely, trying to understand in our early formation of our solar system. So this is sort of the kickoff of the main body point of the talk tonight. In 2000, late 2022, I think it's actually published in 2023 in Astronomy and Astrophysics. And here's the link. It's actually a couple Japanese authors put a paper out here to go back and revisit this idea of our sun and its birth cluster. Okay. So previous studies, which I don't show, um, people have been looking at this, and what they're looking at is they're trying to explain this idea of a mix of aluminum, radioactive aluminum, that's aluminum 26, like rich and poor. They're called calcium aluminum rich inclusions. The CAI is the short term. Those are the earliest elemental, like think of elements of calcium and aluminum kind of floating, I wouldn't say like by themselves, but maybe connected a little bit. But those eventually get formed into rocks in the crustal layers and things like that. But they can measure through, like I said, through the actual samples, through meteorites and actual spacecraft sampling dust in the solar system and studying those daughter products. Right, it's well known that there's a mixed match, and so the idea is pointing very strongly that can only come from, you can only get this heavy aluminum. Aluminum's pretty far up on the periodic table of elements. You can only get that from something that can produce heavy elements, and that can only come from a core collapse supernova, right? A type 2 supernova. And so because they're included in these CAIs, the inclusions, they know, because those are the earliest elemental facets of our solar system, right? The general consensus is that happened in the first 100,000 years. And so what this whole paper is about is these guys created some models to predict um, like the type of stars that you would have, how close it would need to be to produce the abundances of aluminum 26 that we can infer from these material samples. And so they produce this. This is sort of a cartoon of all the math that went into their model. So I'm going to try to explain this. Um, so on the bottom is a timeline that goes from zero. It says TSF. That's time of star formation, right? So when you have a giant molecular cloud that gets perturbed somehow, and once gravity starts working, stars start, material starts connecting and forming stars. And so you can think of these two bottom rows here, this red star and then these solar type stars, right? They're all, imagine this big cloud, and it's condensing, right? And gravity's clumping things together, and when it gets big enough, right, eventually stars will start to form. Well, the bigger there are, the stronger the gravity, and the quicker they can form. And so that's happening in parallel to maybe smaller stars, right? You kind of have a mix of stars, right? It's all random on how these things pull together. But the idea is, what's the probability that at least one supernova was close enough to our sun, wherever it was in the cloud, that it happened within the time frame of these massive stars, um, and happening at a time when our sun was just beginning, right, in the first 100,000 years. Um, I don't know if you guys remember, but astronomy, but the bigger the stars are, the smaller their lifetimes, right? They're hotter, they're bigger, they're more massive, right? They think of gravity. It's hot, a lot more higher core temperature. It burns the fuel faster. So stars in the range of 20 to 60 solar masses, their lifetimes are only like 4 million years or less, right? Whereas our sun, the lifetime's 10 billion years, right? So these are pretty massive stars. And so they have violent explosions and produce a big flux of heavy elements that can be injected into our solar system. And then these couple cartoons here. This is all still active area of research, but the model was to show that it can happen, and this could happen right before the cloud condenses to form our star. So the aluminum 26 is in this cloud, or it could have happened right after, where our star is already kind of formed and it already has sort of a circumstellar disk, and it could be injected into that too. So they don't know really about that, but we do know, um, you have to explain this influx of aluminum 26, and so that's what the idea of this model is. And I'm not going to go through all the math and everything, but here are the main results to sort of explain some of this. Now, both of these graphs are kind of saying the same thing. PSN is the probability of at least one supernova, right? Core collapse supernova. In the horizontal axis is NCL. That's the number. Okay, like I said, all these stars are forming in a cluster, so it's the number of stars in a cluster, right? What's taken into account in these models is we understand nuclear fusion and the fusion rates of stars, right? It's called stellar nucleosynthesis. Um, and given the mass of a star, they have a pretty good idea of how much elements they can produce, right? And the time it takes and so forth. And so building in all that, all the processes and the separation, the average separation of stars in a cluster, you can basically make these predictions. And so if a cloud takes, so you have the time of star formation from 5 to 12 million years. That's what these colored lines are. And so the way you read this, what it's showing here basically, and it's the main conclusion of the paper, for a probability of 50%, if you that's right here where my cursor is on the left vertical axis, and if you just read over to the blue line and come down, it's at around 20,000, right? So what that's saying is the probability of the direct injection of short-lived radioisotopes from a supernova is 50% when the initial size of the cluster is 20,000 stars. And then the plot here on the right is it's just inverting the probability and the time of stellar formation. But it gives the same number, just in a different way. So through the results of all this work, they've sort of built on and revisited this, right? This was done only, 3 years ago. Previous studies before had showed, they were thinking maybe a cluster of 1,000 stars or so. Now you may be wondering, well, how do we know? There's a whole range of star formations, time frames, right? This is the time it would take a molecular cloud to formulate all the stars, and so that's an active unknown. It could be as high as 12 million years. It's the consensus out there, is that it's probably closer to 5 million years. I kind of did some Google searches when I knew about this talk coming up again, and I haven't seen any sort of improvements on it. I've seen ranges from 2 to 4. It can be as high as 10, right? So let's say it's 12 million years, right? And so what that would mean, if you wanted a 50% probability, you go to the gray curve, and it's about 1,000 stars. Um, so that's still higher than previous estimates. So what this paper is really showing us is um, the whatever cluster our sun came from, there's more stars in it than previously thought. So that's one conclusion. Um, the That's sort of what these two bullets here are. All right, the injection of aluminum 26 materials into the solar system formed from a nearby core collapse supernova have occurred within the first 100,000 years of the solar system's existence. And remember, this is just probability of at least one, because that's all you need, right? You could have more, and that might explain, right? Let's say, other conditions aren't in place, but maybe there was more than one. But the chances of two being close by the first 100,000 years seems kind of small, but it could happen. But the point was they wanted one's enough to help explain this flux of aluminum 26. And what they've also concluded here, and I kind of assumed it when I was explaining it, but it's really studied in this paper because they looked at all solar masses, right? Anything above 8 solar masses is large enough that can eventually go to supernova. Um, you know, our sun won't be a supernova. It'll go through a red giant phase, shed its atmosphere, go through the AGB phase, eventually come down to a white dwarf phase, and then just cool off as forever, until it becomes a black dwarf. So it does not do core collapse supernova. So that's one key takeaway is this new research is saying, hey, the birth cluster is much bigger than what we thought, maybe 10% or 100 times. Now, so that's one key factor to think about. Um, Again, mainstream science is looking at this. So going back to our table of these higher than normal abundances. Uh, so on the left, I'm kind of pointing out because I want to pick on uranium and thorium. Um, uh, you may know from if you follow some of the RTB resources and other geologic resources that uranium, thorium, and potassium are all radioactive elements in our crustal in the Earth's crust, right? That forms the background radiation. But deeper in the core of the Earth is uranium and thorium, and that drives the not only plate tectonics but the geomagnetic field through the heating of the core, which is liquid iron and it's rotating, right? That generates our magnetic field. So without a heated core, you would not be able to have a protective magnetic field. On the right side, again, these are the vital poisons. Just pointing that out here. Um, Now, you could actually go in and every one of these and kind of try to do a deep dive. So what I looked at was let's look at aluminum for a minute. The top one says 40 times more. Well, what do we know of that's important on life for life on Earth that deals with aluminum? So you may have heard of the carbonate silicate process. Um, it's it's a long standing process. Like when I say long, throughout all of geologic history of the Earth, it's a way that the Earth it's like a feedback loop that continuously scrubs and maintains our carbon dioxide levels. And on the right is sort of the quick overview of it. But essentially, um, carbon dioxide in the air, that's CO2, right? It gets dissolved in rainwater, it falls down on the land. It interacts with the silicates on the Earth's surface, creates some byproducts that contain some of that same carbon. And eventually, it makes its way down into the ocean, settles on the seafloor, right? And then we have plate tectonics that have to subduct to each other, and it kind of pulls it under and goes back into lava, right? And then some of that it may be re-released through volcanoes, right? And then the whole process is it's just continuously going on. And so what I'm not really showing on here or talking about much is you need organisms and in place to help expose those silicates, right? That helps drive some of this process. So life's involved in this feedback loop, and then what I'm really getting at is on these plate tectonics, right? I talked about aluminum. So what does aluminum have to do here? Well, there's a substance on these plates, it's called aluminous orthopyroxene, and this is the chemical formula. And the X can be other elements attached to this chain, but aluminum's in this. And I even put the paper here if you're interested. But this aluminous orthopyroxene plays an important role in allowing plates to slide past each other, right? If you think about it, when a plate's coming on one onto the other, um, especially in California, right, near fault zones, right? You guys are well aware of earthquakes and things like that, but there's a lot of friction that happens from there. And so, uh, depending on how violent the plate's movement, it really determines the like the level, the strength of the earthquakes and things like that. But down on everywhere else around the earth, right? Um, this aluminous orthopyroxene helps the plates. I would say like lubricate, right? That's kind of like a word to think about. It really does help on the efficiency to help minimize um, some of that geologic activity. And so just one of these, I'm just like it's trying to say, if you go back to these elements, right, each one of these plays a major role um, in some facet of talking about the importance of life on Earth. And so I'm not sure how many of you like geology, right? This particular talk, right, we were talking about everything. We went from planets, stars, galaxies. Now we're talking about elements and geology, right? So it's all interlinked, and and it's pretty powerful stuff. Any questions on any of that? Let me just pause there for a second.
Yeah, I've got a question, Brandon, is I'm trying to figure out, maybe you go over again how the number of stars that it took to form our sun has to do, how does that relate to things like how much aluminum we have?
Okay, it was hard to hear you, but I think you said the question was like, how does the number of stars in a cluster eventually
Yes.
relate to how much aluminum?
Yeah, sorry, we had a microphone problem here. Can you hear me
I
better now?
Yeah, definitely. Yeah.
Okay, sorry about that. Yeah, so I'm just trying to make the connection between the number of stars that it took to form our sun, because I think you were saying it's much more than what we thought
Yeah,
originally.
yeah. Okay. So, yeah, let me back up here.
Right,
Some,
how that connects to more aluminum. Yeah.
yeah, yeah. Okay, what I'm trying to say, it's not necessarily the number of stars. Uh, so the size of the cluster, if you think about it this way, if you have a larger cluster, you have more stars in it, you're going to have more chances of a mass of a massive star being close to the sun than you would in a smaller cluster, right? And so the idea was what what is the minimum size cluster, like this research here, what they determined was the a cluster of a size, let's say 20,000 stars, has a 50% chance, 50% chance of having a very large star next to our solar system, but with a mass 20 to 60 times, right? That's the type that's needed that can produce aluminum 26. That that is close enough that could produce the abundance of aluminum that we find in our solar system. So basically, it's not. I'm not trying to say that the size of the cluster determines um, like how much aluminum we have. It's really the number of what's the likelihood of just one star producing that, right? If the cluster is too small, Um, so like, look, if you follow these curves, if you go to the left on this horizontal axis, right, the probability goes it quickly comes down, and if you really were to plot this on a log scale, right, it'd be very small probability. So what it's trying to say is you can't have a cluster of 10 to 100 stars. Like our sun is not likely to have been formed because the probability of a supernova, like if it's a 5 million year, right? I mean, I can't even see this line here. It's like less than like 1% chance or something.
Okay,
So
so I think what you're saying is that it has to do with the supernova, and in order to get the aluminum, you have to have a supernova happen in order to get that aluminum.
right, right. And you're more likely for that to happen in large clusters. Now, what I
Right.
didn't show you, I'm going to talk a little bit more here in a second. Um, it's actually on some of my concluding charts, but when you look at these clusters like this, uh, when we look around, so there's only maybe there's like thousands of clusters. Most of them are these little open clusters. There's only maybe 150 that have 10,000 or more stars in them. So if this is true, right now, this is all active research. That's sort of the caveat, but this is kind of where it's leading. It's saying, you know, um, our our solar system probably formed closer in where the metallicity was high from a uh, cluster, kind of like one of these, probably more like maybe like this or smaller. I think these have more than 10,000 stars. So it'd be a little bit smaller than these, but not like this on the far right. And so the point is not only uh, are all those galactic conditions in place, but we probably needed to have formed in a certain type cluster to account, and it had to be the right type of cluster to give us the right probability of a supernova producing close enough that can produce this inject all of these elements into our solar system.
Okay, I think I got it. Tim, did you want to ask something now, or do you want to wait? Go ahead. We got another question.
Yeah,
So the uh, carbonic acid rain that he was talking about, is that the kind of rain that's people have complained about historically, that's been destroying statues and stuff?
I think it's related. Yeah, I think it's related to that because yeah, CO2 dissolves in rainwater, right? And so yeah, that's the carbonic acid rain. Now and it can be even low concentrations. I didn't show the full chemical formulas, but when you do CO2 plus H2O plus the silicates, um, these things I have listed here on the second bullet in this box on the right, those are the products, right? Once it interacts, actually, here's the chemical formulas on the left, right? So the you have carbon dioxide plus water plus silicate. Calcium CaSiO3 is most of the silicates on the surface, plus weathering, right? That's the key thing. The weathering, not only natural weathering, but life forms helping expose, uh, you know, life like churning up dirt and rocks and stuff, right? That plays a part of it, right? That it if you didn't have life and they're doing that, it probably wouldn't be as an efficient process. But yeah, that produces calcium, 2HCO3. I'm not sure what that is, and plus sand, right? SiO2. And then all these things eventually, through rainwater, rivers, I mean, we're talking over geologic time. It's a very slow process, but it's called the carbonate silicate process, and you should look it up. It's actually pretty interesting.
So we can say, thank God for acid rain. He's
Yeah,
cleaning the air. So sort of like the old
yeah,
joke, what does
yeah,
God use to clean the oceans?
yeah. That's the more we look at things, there's really, even though we find the bad things, there's also good in a lot of these things too, right? And so, yeah, that's a great point you made. Right, because without that, we would not have a Earth would probably be, even though we're kind of on the inner edge of the habitable zone, the liquid water habitable zone, we might have we would probably have a greenhouse effect, right? We're really close to having that right now, but without all the CO man-made stuff, right? Naturally speaking, I think we're really close to being in the greenhouse zone. We're inside the habitable zone, but we're just barely in it. And so something, right? The reason why I also talk about this, and I don't really talk about it in this slide, if this is acting over geologic time, okay, we know our sun was 20 something percent less luminous, 3 billion years ago, right? Once nuclear fusion process kicked off on the sun, our sun's steadily been increasing in luminosity, right? That's how much energy it's putting out. So if the atmosphere didn't change, right, the atmosphere can trap the energy. So we have to remove carbon dioxide. Otherwise, we would not have a stable temperature for a long period on the Earth. They call that the faint sun paradox also. Faint young sun paradox, right? The question is how does life how does the temperature on Earth be relatively constant for all of the period that we know life's been on Earth when we had the sun increasing in luminosity? Well, the big answer is this carbonate silicate process. Kind of going back to the talk, so what is this? We're talking about all this crazy stuff, but really, what's the significance? Again, I'm trying to keep this outside of the realm of religion to tell you, hey, or not that it belongs there, but I'm saying these are real science papers, right? That's why I'm putting these pictures of the journal articles. You can go look these up. This is active research, right? The discovery of short-lived radioisotopes in chondrites, those are meteorites, right, has bigger implications. And it says provides important constraints to our solar birthplace. The rapid decay and high abundance of aluminum 26 produces enough heat to melt and differentiate planetesimals at early times. So this is a huge factor for exoplanet research, right? When we're talking about habitability, so we know solar systems form and there's a lot of volatiles, right? Those are kind of the light gases and elements. And aluminum 26 is radioactive. That means it's decaying and it's emitting gamma rays and electrons that are very energetic, right? It decays to magnesium, a stable form, but it's producing energy, which turns to heat. So you have to have just the right amount of that so you don't burn away all your hydrogen, which is the very lightest element, right? Because you need hydrogen for water. So that affects the water content of exoplanets. It affected the water content in our early solar system, right? And that in turn, right, affects this particular author, John Williams, the capacity to host technological civilizations. Too little water would be inhospitable to life, but too much water covering all the land would prohibit technological development. This is widely, accepted out there. So you have all the implications from this now, right? Not only do you have the physical benefits, on our planet, like in the case of aluminum and some of these other things, but uranium, thorium, and so forth. But you also it constrains factors that affect life. Another paper. Anthropic selection of a solar system with a high aluminum 26 to 27 ratio, implications and possible mechanism. Right? If you look at the top right, these are quotes from their paper. Right? They talk about a ratio of almost 500,000 difference between the ratio of aluminum 26. Aluminum 27 is normal aluminum, right? Like you look at the aluminum in a car frame or something, right? That's stable aluminum. That's what's used in a lot of our metals. The author said it's difficult to produce in models of star formation. So they don't understand, like if you didn't have if you didn't account, like if you just have a solar system by itself and try to run things, you can't adjust all the knobs to make it come out to this ratio. You need some other way to do that. And he says, we suggest that the volatile loss of heating of planetesimal favors future development of technological civilizations and solar systems with elevated concentrations of the radioactive aluminum. That's just like what that previous paper talked about, right? There, independent authors saying the same thing. This has huge implications for early solar system formation. And on the center at the bottom, this was sort of near the very end of the paper, and I thought it was very interesting. It seems clear that the problem lies in accounting for an unusually high aluminum 26 to 27 ratio early in the solar system, suggesting that anthropic selection is a plausible explanation, while erasure and coincidence are not. All right, so they're befuddled by this, and it's quite interesting. Now, this again is from 2009, but I'm not seeing a lot of updates. This is going to take some time to resolve, but I think we kind of understand what the answer is. I think the evidence, the likelihood is, probably closer in a so in a actually I'm going to summarize it here, but I have a few pages of conclusions here. So from previous talks, right? This is sort of conclusions really from all the talks, but really culminating in this particular topic that we've talked about. So we're near the co-rotation radius. The study of Earth and the elemental abundance show, number one, Earth has a unique set of abundances, right? A lot of those are required for life. If they're different, we wouldn't either life wouldn't work the way it does or wouldn't be here, right? The solar system was not formed at its current location because we know the metallicity quite well and our distance from the galaxy. The only way you can get a higher metallicity is if it was further in. I guess it's possible you could say, hey, maybe it was a much bigger cluster that had a lot of supernovas, but I haven't seen a single paper that really covers that. So I think the consensus is, like most stellar systems, they're formed in clusters, and they get bumped out somehow through gravitational interactions. Recent research suggests that our solar system may have formed in a star cluster of up to about 20,000 stars. It could be lower, but it's certainly much higher than what they thought previously. And it accounts for the gravitational interactions that create these trans-Neptunian objects. I didn't talk a lot about that, but these are observations that any model would have to explain. But certainly the elemental abundance it accounts for. We also know that a cluster of 20,000 stars, when you consider all the clusters in the Milky Way, is pretty rare. There's only like 150 that have that many stars, 10,000 or more. This picture on the left is NGC 6139. This is a real image from the Hubble Space Telescope. But this is showing a cluster in the range that we're trying to look at. So potentially our sun could have been in one of these clusters nearby a high mass star that infused all that aluminum 26 and other elements. So yeah, these elements were infused. I'm reading bullet 4 here. We have higher levels of aluminum and certainly all the other isotopes, right? There's so many to talk about, but this one was neat because aluminum, as I talked about, affects plate tectonics, right? And it's just trying to connect the dots of something seemingly unimportant early on, not only affects the water content in the early solar system, but also plate tectonics once a planet forms. And then the famous ones are certainly the very high levels of uranium and thorium, right? Those are needed. I didn't go into the details, but we have to have those if we want a protective magnetic field for a long period of time and plate tectonics. So, a little bit of change of pace here. I know there's a lot of text here. This is Carl Sagan's pale blue dot speech. I don't know if you guys remember this or are familiar. The picture on the right. Okay, so when Voyager 1 was heading out of the solar system, if you remember, it went by Jupiter, then Saturn, and I think it did Uranus, and then went out. Both of these guys are outside of our heliosphere now. But back in 1990, Carl Sagan and some other scientists said, hey, let's point the camera back and look at planet Earth. And this is the actual picture. Earth is that dot. Hopefully you can see it. I'm not sure how well it comes on your screen, but there's a streamer on the right that's reflections in the camera of the sun. But that dot in there is Earth as viewed from within, near Saturn and near the rings. And so that inspired Carl Sagan to have this famous speech that I encourage you to look it up on YouTube because, he was a hero of mine growing up, not knowing that I really cherished what he said about science because he inspired a sense of wonder and all that. But at the same time, I had no idea he was promoting something contrary to what Christianity says. And that is, and I've only highlighted the subsection of the speech. He says, our posturings, our imagined self-importance, the delusion that we have some privileged position in the universe, are challenged by this point of pale light. Our planet is a lonely speck in the great enveloping cosmic dark. In our obscurity and all this vastness, there is no hint that help will come from elsewhere to save us from ourselves. The Earth is the only world we know so far to harbor life. There is nowhere else, at least in the near future, to which our species could migrate. Visit, yes. Settle, not yet. Like it or not, for the moment, the Earth is where we make our stand. And so for me, this, it's a very dismal speech because as Christians, we know there's a lot of purpose. And certainly, I hope to have given you a good sense of flavor that Earth is more than, it's not a speck out by itself, right? It's carefully placed there. There's so many conditions, and we don't see any other, we've found 6,000 planets, and, that's just the tip of the iceberg, but none of them have come close to having all the right conditions that Earth has. And so, through these three presentations, right, the evidence from astronomy, and now we're talking about geology, and I didn't even talk about the biological effects and all these elements and things like that. I mean, we can have a few conclusions here. Number one, this speech from Carl Sagan, right? Or, he was a famous astronomer. I think he was atheist, but he certainly didn't see God in any of this. And the opposite of what he said is really what we're seeing, right? Earth is in a privileged position. There's an extraordinary and inexplicable degree of positioning, order, and timing of our solar system and the Earth, right? We're part of that, right? That formation needed in order to support advanced life. And so with that, you guys have probably heard of this teleological argument for, an argument for God through design. And so this is a form I propose. It's a longer one, but it's different, but it has two conclusions. Premise one is order and purpose only exists where an intelligent agent has been at work, right? The second premise, the development of Earth and our solar system shows sign of order and purpose. Conclusion one, therefore, the Earth and solar system must have been designed by an intelligent agent. And then a third premise could be added to this to extend the typical argument. God is the only intelligent agent capable of designing planets that can host advanced life. And then the conclusion, therefore, God exists. So for all these conclusions to be, for not to be true, right, the premises one or more would have to be shown to be untrue. And so that's a challenge, right? This doesn't, we're showing a lot of factors, and yeah, a lot of them might be able to be explained in some cases naturally, but collectively taking all these together builds a massive cumulative case for design. And so, um, just something to think about. I wanted to leave you guys with that. And then finally, just to conclude, uh, when I was doing this presentation or writing this up, yeah, I couldn't help but think of Romans 1:19 through 20. For what can be known about God is plain to them, because God has shown it to them. For his invisible attributes, namely his eternal power and divine nature, have clearly have been clearly perceived ever since the creation of the world, in the things that have been made, so that they were without excuse. And so I think that's my conclusion. And I know I covered quite a bit of things. I kind of left it open ended with there's so many more topics you could explore connected to this. Um, I think science is this is a lot of active research, especially with exoplanet research. Um, so there's more to come. But I think, as Hugh Ross says, for a while, RTV used to they kept a tabulation of design parameters, and it only grows every couple years, right? Every time they did it, it grew. I remember one point it was 400. Last time I heard it was like a 900 or 1,000. So this is just a small subset, but I hope you enjoyed that, and hopefully it wasn't too technical. I was a little bit worried about that, but hopefully that made some sense to you guys.
Thank you, Brandon. That was really an interesting and challenging presentation. It's seen the sun then and the sun now having to be near the center of the galaxy and then being kicked out to the precise area that's near the um,
Yeah.
co-rotation rate or coaxial rate
Yeah.
location. Yeah, that's
And just so you know, this might be a little bit exaggerated. We don't know how far in it was, but it would have had to been connected to a spiral arm. So that's like the next one in, but so it could be close. I don't know, but yeah, it's it's TBD, right? It's more we may never know that. That's going to be a really hard question to answer.
yeah. You were saying the ejection of the solar system to where it is now was due to gravitational factors. Um, and I imagine that's not reproducible. You couldn't see what it would have been,
Right.
4
Yeah.
billion years ago or what have
Yeah.
you.
I mean, that's exactly it, right? I mean, even if we could like reproduce it, right? It's the time scale, even for something that large, right, is probably on a human time scale, right? It'd be hard to see that over a lifetime. Or it could have been done by divine intervention, right? I'm not to say, it's all pure natural processes, but it could be, right? It's in the realm of physics. I think this is pretty well understood, and you know, a, any space that has a lot of bodies connected to it, right? Gravity affects on that. We see that in the asteroid belts, right? They kick out asteroids all the time, or comets, right? Any questions?
Has anyone tried to model this about how it would work, or is it just too
I
random of a process to
no,
really model it?
honestly, that's a good question. I don't know. I would suspect that people probably have. I don't recall coming across it, but most of my searches was really I was kind of digging into the elemental part of it and the metallicity and those kind of interests. But yeah, I think we would have to kind of look into that. But it wouldn't surprise me. I think we certainly have the capability to do that, right? If we can model the large scale structure of our universe, I think, I mean, yeah, this is a highly dynamic system, but I think it could be modeled.
I was noticing on the elements that carbon and nitrogen were much less than we would expect, and the heavier elements were much greater, which I presume is because the injection of those heavier metallicity compounds
Yeah.
into the
Yeah, I'm trying to scroll
solar
back to it here real quick. Yeah, carbon, I knew. So remember, so this is relative to life. Um, So there's okay. So I guess I need to be a little bit more careful here. So this is carbon, I believe, found in life. Like if you look at the amount of carbon in life versus carbon in uh like Earth's crust or something, that's a little bit different. The elements here on the right are abundances related to life.
Hmm, okay.
Um, but you're right, nitrogen and carbon are they stand out quite a bit less, right? That couple orders of magnitude higher than the rest of them. So yeah, these are good topics, right? That maybe that might be worth pursuing to dig into that a little bit more. Um,
Is
I
there a reason? Is there a reason why oxygen isn't on your list here somewhere? Is that I
uh
didn't notice it.
yeah, I took these out of the Hugh Ross's book. I tried to look up. Let's see. Yeah, it was from Improbable Planet. I think he talks about this or references it in Design to the Core, but I don't think oxygen either there's not really a significant deviation or he just didn't address it. But I don't recall hearing that it's much different or seeing much difference. But I honestly I don't know. I'd have to go look at that one. That's a good question.
And this may be a tedious question, but I
Yeah.
noticed that silver is 610 times more and gold is 5 times less. Is there a good explanation for that, or is that just a circumstance?
Yeah, that's just the way it is. Again, these are estimates. So 3 and 5 aren't really hugely different, you know. Um, those are just going with the raw abundances and scaling them to the magnesium. So, I mean, for me, I would just read that, that it's effectively the same. I mean, uh, there's not a huge difference between 3 and 5, but um, gold's much different than silver on the periodic table of elements. So it's harder I mean, it's much heavier, right? So
Mhm.
supernovas are going to produce less gold than um, silver, which seems opposite, right? But um, yeah, that's a good question. Is that what you're getting at? I guess.
Well, I'm just more of a curiosity.
Yeah,
It may not
yeah.
be
I
a
think
significant question, but it may be related to what we do need here on the earth in terms of
well, there's that,
oxygen.
and then like I didn't touch upon if you remember in the early papers, right? There's some elements that coming in from these AGB stars.
Hmm.
Where's the paper here? Sorry for this. It's on the papers. It's right here. Um, it, right. So you have to look at the contributions from intermediate mass AGB stars. Those could be produced in some of the silver. Oops. Yeah. The low mass AGB stars can't produce the really heavy stuff like iron or higher, iron and higher probably. Um, but potentially I'd have to go back and look, but I think they're contributing, at the mid mass range, right? Like silver, magnesium, manganese. Yeah, I mean, I don't think, we have Hugh Ross is the first I've seen to really kind of try to start explaining a lot of these abundances. And it can only be so good as what the measurements reveal. So I think, there are some error bars on these. And so when we look at that table, you know, to me, 3 and 5 is effectively kind of the same. I would look at more like order of magnitude differences, like 10 and 20, or 20 and 100, right? Those are the kind of differences that require some kind of explanation.
Okay, thanks.
But yeah, those are good questions. Yeah, you could spend a lifetime researching a lot of these.
I'm curious about the term in the one quote, anthropic selection. I was wondering, when a secular scientist is forced to or chooses to use that term, exactly what are they talking about and what's implied for them?
Yeah, I mean that's a good question. You know, some you know, like Christians would look at that to say, hey, these are needed for life, as imposed from, let's say, a divine source or something, right? Um, whereas some scientists who don't look at that way, they might just say, hey, it's a selection effect that we're here to see it, you know, therefore we can only see what we see. It's just we're here to see it, right? So I don't know in this guy's particular case, but he's clearly you could tell by the nature of his sentence that he he's sort of mandating that there, number one, there's a problem and it can't be coincidence. You know what I'm saying? He's just not going that one step further. Yeah, in a paper like this, they wouldn't talk like he wouldn't go into the philosophical side of this. I just did find it interesting that this sentence fragment was in there, though.
Back to the list of the 22 vital poisons, I would suggest that the reason oxygen is not on that table is because it's not listed as a poison. Uh, you get a little more oxygen. Well, maybe you can start your fires better on a rainy day, but
Yeah, yeah,
you
yeah.
get
That's actually a good point.
you get a
Yeah.
little more fluorine. I can think of few things more terrifying in a lab to me than hydrofluoric acid.
Oh, yeah.
So
Yeah, that's I think you have a good point there.
to
That
me,
could be why. Yeah.
what this table is a description of is the incredible fine tuning that our star and solar system had to go through without without getting an outside balance of all of these very poisonous things. And I'd like to see an extension on the table or a different table that would say, how close are we to being too poisonous for iodine or nickel?
Yeah.
That
Yeah. I mean, I think that's you know, obviously we're not prepared to do it here, but yeah, I think there is data out there that we could probably research this and find out, like for every one of these, right? Look at all these factors to see, like you said, are we on the very edge, borderline on these not being good for us or not? And then look at the cumulative effect of just that alone, right? Um, yeah, that would be interesting. They so I have, reasons to believe, I think recently updated their website, but all their articles are still on there. I think if you go in and do searches on vital poisons, I think he has some more articles. And he may go into that on some of individual ones. I'm not sure. That may
I,
be worth looking into.
I got a question. You were talking about how there's only like 150 clusters in our galaxy that have 10,000 stars or more.
Yeah.
Um, so I guess the significance of that is that it'd be very rare to actually have a star that's actually has been close enough to one of these supernova, right? That's like the implication of that.
Yeah, yeah, because if you think about it, if you go to let me look at this picture here to help visualize it. So the top right is a typical cluster, an open cluster. Most of them are open clusters, and there's
Right.
probably thousands of them. I'm not sure, but there's a lot. Um, most of these have tens to hundreds of stars versus thousands on globular
Right.
types. So yeah, it's rare. Like if you're just counting the number of clusters available in a Milky Way, right? Um, you know, uh, I don't know what the actual number is, but let's say 150 over a couple thousand, maybe 10,000. I'm not sure, but right, that's the point that's being made is
Right.
if indeed the sun was came out of a larger cluster, which it seems like what these papers are indicating, um, that's a little bit rare because most stars are formed in open clusters.
So we're looking at how many clusters there are now of that size.
Yeah,
When what, 5 billion years ago or 4.5 billion, whatever, that many billion years ago, would there have been the same number of clusters or could it have been a lot?
Yeah, yeah, because most of these stars are well, that's a good question. First question, I just wanted to point out this I went back to the paper here. So this paper from 2003 was saying 90% of the stars were formed with only 100 stars or more, right? Okay, um so that's probably the low limit of the open clusters is 100. Now I think a lot of these clusters are okay, so the clusters are all about the same distance, right? From Earth, but within the cluster you have a variation of stars. So all the high mass stars burn their fuels out quite quickly, but all the stars that are M type stars and all that were around, maybe 8-10 billion years ago. And so it really depends on the type of stars in there, but many of them, they probably still were around. Um, the smaller open clusters are more likely to have dissipated some, and then there's new ones. For instance, the Pleiades, right? We can go out on a winter night and look up near Taurus, and you see the Pleiades. It looks like a little Big Dipper kind of thing,
Yep.
right? That's a young star cluster, right? That's an open cluster, but those are all relatively new stars. So I think these globulars are typically older, so that would give credence to an old solar, like something like as old as our sun and our solar system, 5 billion years, to have come from some one of these older types also.
So I think I'm missing something in my understanding of how the star forms. You've got either 100 or 10,000 stars in this cluster. How does that form a star?
No. So okay. The way the stars form is you have a molecular cloud. So just think of a big cloud of hydrogen gas and maybe helium, right? And
Okay.
some dust. They all stars. All of these clusters form from the condensing of that cloud, molecular cloud. And so basically, what that means is you can have a some kind of gravitational perturbation, like maybe something goes by it and get something moving, right? Once something's moving, right, something heavier than its adjacent partner is going to attract it, and then it connects, and then gravity just it's heavier and it starts pulling on more things, and so this is happening in multiple places within the cloud, and all this material condenses, and then each one of those become a star because once it gets heavy enough, gravity it's always trying to pull it tighter and tighter together, and it heats up the core, and it gets so hot that it can eventually kick off nuclear fusion, and that's how stars form.
Okay, so I get the idea of the cloud forming the star. What I
Yeah.
don't get is the connection to the cluster of other stars. Why does a star have to form within a cluster?
Well, they no, so because mo like the paper was saying here, I forgot the title here. 90% of the stars are formed within clusters.
But I guess I'm trying to figure out why. Why can't a
Yeah,
star just form
yeah,
anywhere?
because you're not going to have a small enough cloud that only can produce one star, right? The smallest molecular cloud will produce like I don't know 10 stars or 100 stars or something like that.
Oh, okay, okay. So you got to work backward in time to figure out. Okay,
Yeah,
get
yeah,
it.
yeah.
Okay.
So yeah, I mean, usually these clouds are so big that you're always going to form multiple stars, and that becomes a cluster. Now the question is, how big is it? Is it only have enough material to make, let's say, 100 or more, couple hundred or 1,000 or 10 million? Right? We just don't. That depends on how big the cloud is, right?
So it starts out. We start out with a cloud, this big, huge cloud, and then
Yeah.
within that cloud, there's no stars to begin with, and then that
No.
cloud starts to form lots of
Yeah.
stars. Okay, okay.
Yeah. And it's
Right,
not like
that
it's,
was a missing piece that I didn't quite understand.
oh,
Okay,
I'm
yeah,
sorry. Yeah, maybe I didn't, I never really try to explain that. But yeah, and it's not a magical thing here, right? We're just saying
yeah,
there's just dust and gas, right? Most of the universe is hydrogen, and there's just a chunk of this floating around,
right,
and for some reason, now that's there's a lot of reasons that could initiate it, right? It could
yeah,
bump into another cloud or go by a star, right? It just needs some perturbation, right, to like bump something in there, and then once things start colliding, right, then that's when you have gravity attract starts, and gravity is always sort of attracting,
right.
but something kicks it off, and then yeah, everything forms out of that cloud, and that's typically a cluster of
Okay,
some
yep.
type.
Okay, thanks. I think I got it now.
That's my understanding. No, I think that's pretty much what that's how they do
Yeah.
that. I don't think, honestly, I've never researched it, but I don't think stars can form. You can't have one star form by itself, I don't think. I mean, I guess you could theoretically, but I think
Well, there had to
like
be
they're
a first
saying,
star. There had to be a first star, right?
right, but you have to have the material. The stars are from hydrogen gas, right?
Yeah,
So you need, and there's gas, that's like most of the universe is hydrogen,
yeah.
and dust particles in there, whatever the dust is. I mean, it's it could be remnants of other stars, right? You could have supernova create a shock wave, right? That's the other way, right? That's a common one, is a shock wave from nearby supernovas propagating through the universe that kind of hit a molecular cloud to get that a formation of a star cluster.
But is there any way to know if there's other stars that were formed that, I guess, in a sense, the same situation as ours, but just formed in one part of the galaxy and got kicked out to another part of the galaxy? I mean, is that very common?
Um, I don't.
Is there
I
any
would
way we
think it
need to
is
figure that
common. I
out?
don't know how we would know that. I
I mean, because you got gravitational stuff going all over the place. You think maybe
Yeah, yeah,
kicking things
it's
around might happen a lot. I don't know. It's like
yeah. No,
a
I think
pinball
you're
machine.
right. Yeah, it would be. You'd have to look at. I don't, and maybe there's people that do this, but you'd want to study the metallicity of the star, how close it is to the galactic center in its neighborhood. Also, like just to understand, is it different than the stars around it?
Yeah,
Because
what I was trying to figure out is how is that a design argument or not? The fact that we formed in one place and now we're in another place, or is that very common? So it's
yeah,
really, really
I
anything.
think it might be common, but there's nothing to say. Um, I think the key thing is w- we have all these elements and all this kind of stuff, and we're at the co-rotation radius, or, right at it, right up to it. You know,
Yeah.
um, I
So
don't know if there's a lot of planets that would fit all the, just like if that was like a checklist, right? How many planets would fit in that category?
right. So the fact, so could could there have been a planet, or sorry, could there have been a star that formed in the co-rotation radius that would have which would have these properties? They actually because our star didn't.
Yeah. Well, that's what they think. Yeah, I think anything's possible, but if I do know there is something, it's just like in our solar system. If you're exactly at the co-rotation distance, and there's an exact number, I don't know what it is, but it's around the eight. Like we're just inside of it, right? Like,
uh,
but if you're exactly at it, I think they're called mean motion resonances, and those always get kicked out. Like um, it's just the resonance, gravitational resonances between the spiral arms and the center of the galaxy
yeah, I
builds
can
up,
see.
and that would be enough to sort of bump it one way or another.
Yeah,
And
I could
something
see
like
that.
that's happened in our solar system with Jupiter and Saturn. They've kind of flipped their locations
Right.
a bit because they're two massive bodies and they interact gravitationally around the sun. And there's somewhere rotate like distance um, and periodicity where they sort of add up these gravitational effects, and it's enough to kind of switch them or bump them around.
What I'm trying to figure out is the our star formed, or at least the theory goes that our star formed not in the co-rotation
Right.
distance, but and then it got moved. But could it have formed within the co-rotation distance and not have been moved? Is there any reason to think that, in other words, if it had done that, what would be different now? In other
Well,
words,
then the metallicity would be different because if you
yeah, so
now
why
I
is the
don't
metallicity different just because it's in a different location? Does that mean there's different number of stars in the clusters that it was formed in, or
so so the you'd have to go look at these usually when they measure metallicity they always kind of do it in ratios
right?
but they're looking at oxygen irons and carbons and all that so they've mapped our galaxy quite well like they understand and probably can measure it through observation at the distances so that's kind of where this graph has come from it's been reproduced from this was an older paper but I don't think it's changed much so they understand at the co-rotation what it is. Um, but then when you look at the metallicity of our sun, I don't think it matches that. And the only explanation, because it has a higher number, it has to be formed from uh, closer in.
Do they know the theory behind why there's that particular curve? In other words, why does distance matter to metallicity?
Um, I see what you're saying. Yeah, that's a good question. I know there. I don't know off the top of my head. It has to do. Uh, So remember, metallicity is just sort of the concentration of the elements, right? And
Right.
so they too collect around orbit the galaxy center. But there's also so it gets really complicated, right? You have the galactic center kind of holding them in a particular orbit. You got the orbital velocity of these things, but then you have the spiral arms that are interacting in a certain way. And so I think when you put all those things together, it kind of builds this weird looking curve. I'm sure there's other factors too.
Would that curve be the same for other spiral galaxies? I mean,
Um,
similar?
it might be different because not so the thing is not all spirals are symmetric, right? So that's what I was trying to say earlier.
Right.
Like we live in a barred spiral galaxy. There's like 8 different spiral types, so the centers are all going to be different. Some have more spiral arms than two big ones like we have. So I think, theoretically, if there was another galaxy like ours, it could look like that.
Okay.
But it also depends on the age of the like uh so like okay, so this gets real complicated. Well, I think I tried to talk about in the last talk, and I mentioned it briefly here. Every galaxy cluster um has to have a lot. You have to have the right optimum number of dwarf galaxies orbiting it because it's the dwarf galaxies that
Repeat.
eventually get absorbed, and
Yep.
so those galaxies, depending on their concentration of elements, right, would contribute to the type of elements, in the big galaxy, right? So
Hmm.
so
Yeah.
there's just a lot of factors, but
Sure, I see.
yeah, but I don't know. That's a good question.
Okay.
But I think they're all kind of similar. Um,
Yeah.
Assuming, the processes in the universe are all about the same, right? We know,
Yeah.
you know, it's mostly hydrogen and things like that. It just, I think it's, accounting for the individual shapes and sizes and the gravitational parts of it, how the spirals themselves form. Right now, I don't think elliptical galaxies won't look like this. They have a completely different curve, and same thing with irregulars. I can't remember what the curves look like, but this is measure. I think this particular one was. I think a lot of this was based on actual measurement too.
Sure, sure. I want to make sure I give Tim a chance to ask his question here.
Yeah, go for it.
Go ahead, Tim.
When you said our solar system had to be formed near a supernova, I was a little bit surprised because from what I've heard is that there had to be like at least 4 different types of supernova near our solar system for it to form with the metallicities. And I think the argument that I've heard is that that could only happen near the center or closer to the bar in the galaxy. And that's why, can you comment on that?
Yeah, maybe a little bit. I've never heard that the 4 types you're talking about. Like what I'm not sure how you said that. What I'm trying to say here is what this paper is talking about. We're talking about to account for the aluminum 26 enrichment. It can be explained, like they run these models that within a cluster of couple what 20,000 or maybe a little bit less, you can come up with a decent probability of a massive star given the distance, the spatial separation in a cluster, right? That has to be part of it. um, you can account for that aluminum enrichment for with a solar mass 20 to 60 solar mass star near our sun in the first 100,000 years, right? They're just trying to understand to explain this anomaly. I can't highlight it here, but on the bottom here, oops, this on the second line it says to explain the coexistence of aluminum 26 rich and aluminum 26 poor inclusions in the early solar system. The only way to do that is the only way known explanation right now is that had to have been at least one uh, supernova of a certain size star um, in it, near us, and it presumably in a cluster, right? We don't know if we formed by ourselves, but since most stars are in a cluster, it's reasonable to assume that. And it happened in the first 100,000 years, and it got. Now this is before planets started forming, right? This is either in the molecular cloud right as it's contracting, or in the disk right when you get enough material to kick off the actual sun, and you still have this disk with no planets yet. So the I'm not sure your comment about 4 types of supernova, um, if what you're getting at there, if that's like we know later on, once we had planets, we've had very few supernovas because those are bad for life on Earth once you have life, right? But that's much later on this timeline, on this green timeline.
I'm sure that was from you somewhere along the line.
Yeah, and we do know that there was 3 generation of stars. I'm not sure if that's what you're getting at, but those are just referring to ever since the origin of the universe. Um, I think they call it generation 3 was first. You had the mostly hydrogen type stars because that was the only elements, right? You haven't had enough heavy element production. And so you had these kind of hydrogen based stars that were short lived, and that was sort of like 1 generation of stars, and then there was a second, and then pretty much everything we see now are 3rd generation stars. I'm not sure if you're talking about that because there is some discussion on how you produce the generation of stars given the types of supernovas and the elements that are produced, over time. It might have something to do with that. Maybe is what you're thinking.
No, the generation of the star would be different from that. It's more like, and I have so little understanding of this, but it's not just an argument for the abundance of aluminum. You can solve that with one type of supernova, maybe. But I mean, that doesn't provide everything. It's like fluorine. How do we get so much fluorine? Uh, People
Yeah, I
didn't even
see. Yeah.
understand how fluorine was produced for so long.
Yeah. So that so yeah, I'm mainly focused on aluminum in this paper, but that if you actually go in and look at the paper, they'll talk about, I mean, it's also used to explain um which what's this paper? A lot of these other elements on the second line here, right? And this is not all inclusive, but um yeah, I mean, these are mainly focused on a lot of the heavy elements, but yeah, we do know, for instance, uh, the there's process like you talk about fluorine on white dwarfs being produced from white dwarf stars, right? There's some really weird elements. There's a few things that were produced from other mechanisms, so that might be what you're getting at too. Um, I think I think it's the fluorine being produced on white dwarf stars. And we also now know that the gravitational wave mergers, that neutron star mergers also produce heavy elements. So there's still some more science to be learned and understand what those contributions are with the heavy element production.
Yeah, but still with the fluorine production, that's still not a supernova. So hey,
Yeah.
I know so little, I can't even say what all the kinds of supernova are, and I'm sure we're finding more.
Well, there's only type 1 and 2 supernovas. I think you're probably just saying other stellar interactions. uh, but yeah, I think this is an open area of science, right? We've only recently understood processes of appearing on white dwarfs. I mean, that's very exotic stars that are already dead, but they're um, electrons degenerate. They're very dense, and they have certain processes on them that are different than like a core collapse, like a type 2 supernova. Type 1 supernovas are um, they're not stars blowing up necessarily. It's usually when you have companion stars and one star is sucking the atmosphere, like it's already become a white dwarf, and it's close enough to its companion where it kind of sucks material enough to cause that white dwarf to collapse. And because all white dwarfs are about the same mass, all the type 1 supernovas have like the same light curve, and so those are used as candlesticks. That's how we can measure certain distances in the universe. But so like I'm just trying to say that there are different types of supernovas, but it's usually just the type 1 and 2s. But then there's a bunch of other processes that can still produce heavy elements, and like things like fluorine and stuff like that.
It seems to me that there's really compelling evidence for non-coincidence when you see these unusual factors all coming together. Um, how do you use your argument for design with your colleagues or with people who you're around, and what advice can you give to us?
Well, people are different everywhere, but for me, because I deal with a lot of technical people, I mean, I just try to get them, to think about. I think there's a lot of power in the sort of compounding evidences, like trying to provide uh, data that's not really explained the same way, but still show, um, very like low probability, right? Things that seem to defy the odds, right? From different mechanisms, right? And compounding those together to make a case, right? And um, I like Lane Craig's argument about, you know, you only have chance, necessity, or design. It's easy to explain away the chance. If someone's going to accept that, they have to deal with some pretty bad math numbers that
Hmm.
most, if they're technically inclined, they usually would recognize that seems not likely. A lot of the times they'll just say, they'll acknowledge it and I don't know, just kind of like, yeah, it's, we just don't know, they'll play that card, right? Science, there's more science to come, but I think that argument alone is enough to get maybe some conversation started. But I think you also have to use other arguments um, if you're really going to have a deep conversation, right? There's other arguments that are probably needed, but I think because there's so much quote unquote design evidence, right? I think compounding them is the best way, right? To look at the cumulative effect.
Yeah. The plausibility and the
Yeah,
abduction.
because it becomes ridiculous at some point, and it really does beg a question because it's sooner or later they might recognize it. I mean, it just seems. Let's say, yeah, it's just nature produced it that way. Um, well, why didn't it not happen here or here or here or here, right? And you start getting all these low number probabilities, and then you add other processes, and I mean, it really. I think people are smart enough to see that that starts to become something that can't be held to easily
Yeah.
without themselves having a faith in something else, right?
Yes.
But it's not like that argument's not necessarily. It's just an argument, right? It falls in the family of teleological arguments, but it's really a conversation starter. But what's nice is there's a lot of data to support it, right? It's not like it's an intellect. It's not purely an intellectual, right? There's actual science data to help support the argument.
Yes. Any other questions? Well, thank you, Brandon. This has been very informative and challenging. A lot of things for
Yeah.
me to think about, and I'm sure with more data, hopefully you'll have better understanding as well. So again, I want to thank you so much for your time and expertise, and I hope the tropical storm doesn't get too bad for you there in Houston. And again, we appreciate particularly coming to us a couple time zones ahead. So thanks again.
Yeah, well, I appreciate it. It's always you guys ask really good questions. I don't know everything, but I just hopefully hitting the tip of the iceberg. And, you know, I think you have a really good inquisitive crowd there. I suggest you guys dig into some of this and look at this and track it and see how it evolves over time. But I think um, the fact that you're interested in it is really good. And it's a lot of it's really cool science. So it's a good way just to keep up with science as well and see how that progresses. So, but it's been my pleasure as always. I appreciate it.
Okay. Again, thank you so much. We really appreciate all your.
Okay.
And
Thank you.
Lord bless you and your ministry and your work, and hopefully our paths will cross again.
All right. You guys have a great evening. And until we say hi again, thank you so much.
All right. Thank you so much, Brandon. Yeah. And we will actually be taking a break next month. So summer break, and we'll be back in August. Steve Willing will be here talking about artificial intelligence. So stay tuned.